Hello, Mrs. Farouk. We are from Group 16, and today we will present our project titled Finding the Steepest Path on a Mountain. This project demonstrates how concepts from Calculus 2, particularly gradient and directional derivatives, can be applied to solve a real-world problem. Throughout this presentation, we will explain the mathematical concepts, build a mathematical model, perform calculations, and discuss how these ideas can be used in practical situations. So now, let's jump into the real-world problem. So, imagine that you are hiking on a mountain. You want to reach the summit as quickly as possible, but you are standing at a random location on the mountain. The question is, which direction should you walk to climb uphill the fastest? Although it may seem like you could simply choose any uphill path, there is actually one direction that gives the greatest increase in elevation. This problem is not only important for hikers, but also has many real-world applications. For example, rescue teams need to determine the fastest route to reach people in mountainous areas. Drones use terrain information to plan efficient flight paths, and geographic information systems, or GIS, use similar mathematical techniques to analyze landscapes. Therefore, understanding the steepest path has many practical uses beyond hiking. Next, we will look into the project objectives of this presentation. So, the objective of this project is to demonstrate how Calculus 2 can be used to solve this real-world problem. First, we will introduce the mathematical concepts behind the steepest path. Next, we will construct a mathematical model to represent the mountain. We will then work through a complete numerical example to determine the steepest direction. Finally, we will interpret the results and discuss their practical applications and limitations. Now I will hand over to Song Lejin, who will explain the Calculus 2 concepts used in this project. That is all from me.
Hello, teacher. My name is Song Lejin. My student ID is CST2509037. You can view my personal information in the top right corner of the slide. Next, I will present the second part, explain the mathematical concepts we use in this project. In this part, I will explain detail for multivariable function, and to model a real mountain, we only consider double variables function here, gradient vector, and directional derivative. Also include some subconcepts like partial derivative and unit direction vector. Okay, let's start. As mentioned earlier, we will only discuss double variables functions here. On the slide, we can clearly see the definition of a double variables function. A double variable function is a real-valued function of two real variables that assigns to each ordered pair xy in some set D of the plane a unique real number fxy. If z equals fxy, we call x and y independent variables and z dependent variable. Here we can intuitively see that the graph of a double variables function is often a surface in a three-dimensional coordinate system. That's why we use it to model a mountain. Next is gradient vector. To introduce gradient vectors, we first need to introduce the concept of partial derivative. A partial derivative is the derivative of a function with respect to one variable while keeping all other variables constant. It tells us how the function changes when only one input changes. For example, for double variable function xy, fx measures the change with respect to x, and fy measures the change with respect to y. And we can see the down left corner. There are many different notations for partial derivative. And say we can see the three blue graphs. We can also interpret partial derivative intuitively using this graph. The partial derivatives of f at point ABC are the slopes of the tangents to the curves C1 and C2 at this point. And then if you understand clearly what is a partial derivative, the definition of a gradient vector is very simple for you. It is just based on partial derivative principles. A gradient vector is a vector composed of the partial derivatives of a multivariable function, pointing in the direction of the function's steepest increase or decrease, with its magnitude indicating the rate of that increase or decrease. Next is the final part. I think you might have a question in last part. Why is the direction indicated by the gradient vector always the steepest at a fixed position, and not in any other direction? At this point, we can introduce the concept of directional derivatives. A directional derivative measures the rate at which a function changes at a point in a specified direction. In fact, if we know the gradient vector at a certain position and for the directional derivative in any direction, we all can calculate it using the dot product of the gradient vector and the unit direction vector corresponding to it. And we can see the proof chain in this slide. The directional derivative is maximized when the direction vector is parallel to the gradient vector. That is, the maximum value is obtained in the gradient vector direction, and the magnitude of a gradient vector is the value of the steepest slope. Okay, these are all the mathematical concepts we can use in this project. The next student Wang Haokun will do mathematical modeling and detailed calculations.
So my name is Wang Haokun and my student ID is CST2509043, and I will show the mathematical model of the mountain and the whole calculation of it. So firstly, we can see a graph in the right side of our slide. So it is just a model of the mountain. And from this model, we can see the three key points. The first one is the peak altitude. So the maximum height is 1,000 meters when we achieve 0, comma 0 in the coordinate. And secondly, the minus sign shows a symmetric decay. So it means the mountain goes down as we walk away from the center. Lastly, we see the directional steepness. So because the y number is twice as big as the x number, so the mountain drops twice as fast from north to south than from east to west, just as shown in the graph. So let's look at the math. So here are the first three steps. Step one is the partial derivatives. So we find the slope formulas for both directions by taking simple derivatives. So this gives us the hx equal to minus 0.02x and hy equal to minus 0.04y. And our step two is choosing our anchor position. We're picking a starting point for our hiker at point P, which is 20, 10. And our step three is evaluating the gradient. We put our position number into the slope formulas. So we get the answer is the minus 0.4, comma minus 0.4. So this vector tells us the direction that goes up the fastest. And also is the precise direction of maximum elevation increase. So here are the two final steps. Step 4 is the steepest path direction. We normalize our vector to make it a standard unit vector. So the result is minus 1 divided square root of 2. We can also, it's nearly equal to the minus 0.707. So as a navigational action, this tells the hiker to walk directly southwest to climb the mountain the fastest way. And our final step is step 5, is about the maximum ascent slope. So we find the magnitude. So it's nearly equal to the 0.566. So what does it physically mean? It means that for every 1 meter the hiker moves horizontally, they will go up by 0.566 meters vertically. So you find the best path using simple math, but how does this work in the real world with rocks, trees, or bad weather? Let's hand it over to Suyue. Thank you.
Good afternoon. My name is Su Yue, CST 2509038. Now that we have completed the mathematical calculations, let's look at what these results actually mean. From our calculations, we found that the gradient vector always points in the direction of fastest increase in elevation. This means that if a climber wants to reach higher ground as quickly as possible, following the gradient direction is the most efficient choice. In addition, the magnitude of the gradient tells us how steep the mountain is. A larger gradient means a steeper slope, while a smaller gradient indicates a gentler terrain. On the other hand, moving in opposite direction of gradient gives the steepest descent. Understanding the gradient is not only important in mathematics, but also has many practical applications in the real world. First, for mountain hiking, the gradient helps hikers determine the fastest climbing direction and plan more efficient routes. Second, in research and rescue operations, rescue teams can use terrain information together with gradients to reach higher areas more quickly during emergencies. Third, in drone navigation, gradients can help drones avoid difficult terrain and plan safer and more efficient flight paths. Finally, the Geographic Information Systems, or GIS, use gradient analysis for terrain mapping, land planning, and route optimizations. This example shows that the concepts we learned in Calculus 2 have direct applications beyond the classroom. Although our mathematical model works well, it also has several limitations. First, we assume that the mountain surface is smooth and continuous. However, real mountains are much more complex. Third, obstacles such as rocks, trees, rivers, and cliffs are not included in our model. Third, weather conditions such as rain or strong winds may affect the safest or fastest roads, but these factors are not considered. Finally, different climbers have different physical abilities, which may also influence the best paths. To improve this model, we could use the real terrain elevation data together with GPS and GIS technologies. We could also include weather information and use computer simulations to generate more realistic path planning. In conclusion, our project demonstrates how Calculus 2 can be applied to solve a real-world problem. We learned that the gradient identifies the direction of the steepest ascent, while the directional derivative measures how rapidly the elevation changes in a chosen direction. More importantly, these concepts are widely used in hiking, rescue operations, drone navigation, and geographic information systems. Therefore, calculus is not only a mathematical theory, but also a practical tool for solving real-life challenges. That concludes our presentation. Thank you very much for your attention.